Hello everyone. Very good morning to everyone. This is the class of first CBC class one. You can see that the core our course beyond the curriculum is advanced linear algebra from algebra theory to the modern statistical learning. And you know very well myself, Dr.K.Kavita, working as associate professor in the Department of Basic Science and Mathematics and Humanities in Mathematics Department. Come to the point of the linear algebra is already explained in offline class, and again we are going to learn about that a little bit about that what's the linear algebra again, because in first year and someone you already have seen that here. And here most of the things here goes beyond, so whatever the curriculum is there beyond the things we are going to learn here. So here, linear algebra is a branch of mathematics and used extensively in computer science and engineering. It allows modeling of natural phenomena, linear equations, and efficient computations with such models. Some key applications also we have here. We are going to see in this today's class: computer graphics through matrix transformations, machine learning through the techniques linear regression, PCA methods, that means principal component analysis, and cryptography through integer factorization. Overall, all the linear algebra provides that we can say that fundamental concepts, and it is a tool used across many areas of computer science and engineering. So here, so again, I'm repeating that our course title is Advanced Linear Algebra from Eigen theory to that modern statistical learning. That means in first year you learn that linear algebra, and now you are studying about the COS, computer-related statistical methods. So based on those two, now I'm going to give the course beyond the curriculum now. And here the course discussion is this course provides a transition from standard undergraduate UG program linear algebra to advanced computational theory. It bridges the gap between the abstract mathematical proofs, modern applications for data science, signal processing, and machine learning, etc. Prerequisites also here needed here, the fundamental concepts. So you already studied in first year, vectors and algebraic manipulations and functions. And programming skills also preferably we are going to take because ML is there for Python, and basic machine learning concepts, supervised and unsupervised learning optimization. So this I had given that um, glance about that previously, offline classes. And course objectives to strengthen the students' conceptual understanding of linear algebra beyond that change to H curriculum. And introducing that advanced topics like eigen decomposition, SVD, orthogonality, numerical methods also. And expose the students to, and you can expose the practical applications of LA during that CMI workshop. So that's what you already know about that in last, I think, the SEM1, right? 2-1. Now, the bridge the gap between the theory and real world applications in engineering, data science, computer graphics, signal processing, etc. And you can able to prepare that competitive exams and research and higher studies like enhancing the. You can next further studies. Prepare the students for all these things and developing a strong understanding of the mathematical foundations underlying machine learning, and introducing the students to mathematical principles to optimization and their relevance in data-driven systems, and finally applying row rank approximations, matrix decompositions, optimization techniques to solve real-world engineering and data problems. So this is the syllabus we are going to see that here. First, introduction to linear algebra, and then statistics, vectors. The concepts will be like this: introduction to linear algebra and stats, basic operations on vectors. You already studied in ODE and BC last year. Addition, scalar multiplications, linear combinations, dot product, orthogonality, and projections. Now you are going to see that the add on the now introduction to matrices and matrix vector multiplications also. You can see that with the code. Module 2, Introduction to Stats and Data Analysis and Correlation Analysis, Introduction to Relationships between Variables, concepts of the correlation, positive, negative, and zero correlation, Carl Pearson, CC, Spearman correlation using software tools. Also, in Module 2, we are going to cover this. Module 3, Simple Linear Regression. Again, it takes the 2 hours. Introduction to regression lines and regression coefficients, least square method, simple linear regression models, prediction, estimation, goodness of fit rule. Module 4, Foundations and Advanced Eigentheory, Review of Matrices and Linear Transformations, Characteristic Equations, and Eigenvectors definitions. So here the beyond you are going to see, not that general what used to be algebraic and geometric multiplicity, diagonalization of matrices. Module 5, Advanced Eigentheory and Applications in Engineering. So it takes the three words, symmetric and Hermitian matrices, orthogonal diagonalization, Markov chains, and steady state analysis. How the matrices, symmetric matrices are, TPM matrices will be going to use in stats. Google page rank concept also, electrical networks. Module 6, Modern Applications Beyond Curriculum. It takes the term maximum 4. PCA method, image compression. PCA nothing but in principal component analysis, image compression, quantum computing basics, eigenthesis for face recognition, applications in AI, machine learning, many projects using real data sets. So these are all the textbooks which we are going to see that, and I prepared in the data based on this. Gilbert Strand, Introduction to Linear Algebra. It covers that SVD, spectral decomposition, theoretical foundations. And Trefan and David Bobo numerical linear algebra focus on computational numerical aspects of linear algebra. And Python data analysis also have taken for SAMPy, SciPy, and Pandas. Introduction to Statistical Learnings by James and Michael Hastey and Tich Learning. Reference books also are used. Golub and Charles Van Loan Matrix Computations. James Demel applied numerical linear algebra, online resources, NumPy, and machine learning. Now come to the exact point. Now you can see the applications of the syllabus curriculum. Linear algebra is the basic branch of mathematics that studies vectors, matrices, and linear transformations. Provides a language to describe and solving problems um, involving linear equations, data and signals, geometric transformations, networks, graphs, optimization problems, all these things. I think I covered all these things in a linear algebra in the first class of the when you came in our college, right? So orientation of mathematics. So these are all you aware of that. What's the applications here? There. Moving on to the theoretical circuit analysis using Kirchhoff's laws. So here you can see that how the Kirchhoff laws we are going to convert into matrices. First, let me explain you that what's Kirchhoff laws form system of linear equations that describe the flow of the current, distribution of the voltages in an electrical circuits, how the flow will be there, right? And the matrix solutions. This the matrix solution for network analysis, and matrix techniques are used for the efficient analysis and solutions of the complex network, electrical network, simplifying the process of circuit design and troubleshooting. So like this we can see that we are going to write Ax plus b, say 4y plus z, a x b like this. So here also the a, and then x is I1, I2, I3, I4, and then this is the p, right? Like that we are going to connect. Sound mixing application here will be, you can see that how in music department is going to see that. Suppose you have a track 1, track 2, track 3, taking anything, vocals and guitars and drums, right? And so this is x1, x2, and this is x3. How you are going to mix all these in a single scale and track it at y is equals to alpha 1 or a1 into x1t plus a2 into x2t plus a3 into x3. Y of t is a final mixed song, and a1, a2 are volumes, the gain of all these, and x1, x2, x3 are individual sound segments. Like this we can make it. We can solve the problem like this. Suppose MIC1 records like this, MIC2 records like this, and we are solving that sort of linear equations like this, and we are going to write this is in linear equations form. So we'll get like this. Okay. So that. Moving on to the next application, large language models. Nowadays you can see that LLMs, right? The most of the recent innovations in the arrival of the large language models like the ChatGPT, Gemini, Cloud, etc., whose underlying mechanisms lie in a linear algebra. LLMs are deep learning algorithms that convert text into the vectors. Now you can see that when my daughter also is taking into the AI with all these LLM models, right? analyzing relationships using attention and matrix operations, and generate a new text based on the learning probabilities. So here I presented here like this. What's the element taken into that? Text will be taken into the tokens converted into vectors, which is called embeddings, and the positional encoding also we are going to see, and self-attentions also. Finally, linear transformations. The first come to the text and tokens. The input text is split into small the units, which is called tokens. And each token converted into numerical vector like this, right? High dimensional space using embeddings. And after that, since transformations have no natural sense of order, position also will be required. Right? Position information is added to each vector to preserve word sequence, right? And self-attention, each word, after making into the word, each word components to the words and using them with broad products. And you can use that words like to get a higher weight, helping the model understand context, and many things are there. And linear transformations is nothing but the vectors are passed through matrix multiplications and active of functions like extract measures, then divides at the meaning of at each layer. Next, sixth one, stacking of the transforms, those linear layers will be step 4 and step 5 will be repeated many times in getting into multiple layers to build that they did understand. And the next final output also will be read in the output vector. So using the probability, you know very well probability, again it comes to that wherever you are, right? The final vectors are converted into probability of scores for each possible into next word. Text generation, the predicted word is added to that sentence and the process repeats until the response is completed, right? Moving on to the graphs applications, we can see that a graph I kept here, I pasted here. So which you know that nodes and vertices are already in DS, right? Discrete mathematics already studied. Even in stats also, CYSM also I explained many times. I need not to explain again here. Just we'll see that a graph is a mathematical structure used to model relationships between objects. It is formally defined as a ordered by the vertices and the edges, and V is nothing but the vertices. The set of points or nodes are fundamental units representing the discrete objects. E is nothing but set of links or lines that connect a pair of vertices, simplifying the relationships between connecting between them. And we can see that. So these are all the edges connecting with the vertices, right? Like that. So one example I have taken, incidence matrix I have taken. So edge 1, edge 2, edge 3, and these are all 1, 2, 3 I kept here because for understanding that the matrices, that for, and then coming to the graphs, after that matrices and then solution, right? So you can see that to analyze the graph, first we translate into matrix like this. Adjacent matrix A, and then incidence matrix M, and then next the Laplacian matrix M, whatever that, but we can use that, right? Here from 1 to 2 is there, yes, it's there, but which is negatively, now because we are moving on to that clockwise direction, right? And then from 1 to 2 it's there, and 1 1 any there low, no, so that is not there. And then edge, next 1 2 3, yes, it's there edge, so which is positive. And then 1 2 3, no, which is not there, 0. 1 2 4, no, which is not there, 0. So like that, each and everything we are going to see. So we are following like this clockwise direction, like that. Okay. Next, the graphs. One, applications beyond that, applications and concepts here. Spectral graph theory uses eigenvalues and eigenvectors of graph matrices when classified into that to understanding graph structure. Network analysis, that's what here I kept like that. And the matrix methods helps analyze the complex networks and from social media to chemical structures. Google based on algorithm use the power iteration method to find the principal eigenvector of modify adjacent matrix. This eigenvector represents the importance of the web pages. First, you are searching for the first one related thing only. You are going to get that using page rank algorithm. So whatever you are showing that the interest are making into that likes, right? So based on that, it is going to give you like using the power iteration method. If you like A, you are going to get that A square. That means at the same related. If you like that one and two, that means you are getting that the same thing power A cube, A power 4, like that. So those things. Next, moving on to the network flows applications. I kept here the figures like this. And these we can represent here nodes and loops and branches like that. So this is the actual network diagram. And we can see that here delivery optimization. Companies like Amazon use flow networks to routine the packages through various distribution centers to minimize the delivery time. And water and oil pipeline managing the volume of the liquid moving through a series of pumping stations to prevent that the pipe burst while getting into dam. This is very important in industry. And electrical grids, modeling of the distribution of the electricity from power plants to the homes. This is also important. So these two related networks and this is related to um, the companies, right? Now, moving on to the robotics motion. So here also I kept that very small thing. Robotic motion and mechanics. Matrices facilitate the representation and calculations of the positions, orientations, and transformations of robot joints and the links and crucial for precise motion planning and control. So this is the hand-based thing and TJ, TJ2, TJ, and then this is the base of the matrix, right? So the hand, how it is going to move from hand to the base, no? We can see that L0, L1, L2, L3, right? And J1, J2, J3, and Q1, Q2, Q3. These are all the points, right? Based on that, we have taken that the T-based matrix. So cos Q1 minus sin Q1. So when you add it, the translation is 0. So this translation is like that. We can check that signal processing. So signal processing, you can see that here. These signals can take many forms, including sound waves, images, time varying measurements, values, and data collected from various sensors. And signal processing is a crucial for interpreting electrodiagrams and the ECGs, CT scans, MRIs, and all those things. Analyze the biomechanical systems. Reduces of telecommunication signals such as radio waves also. Audio and speech processing also. Image enhancements, radar, and sonar systems. Containing the C, signal processing also involves that analysis, interpretation, manipulation of signals, which convey information about the behavior and attitudes of some phenomena. Already we see that in Unit 5 stochastic process, these things I explained very clearly, right? So adding more matter here. These signals can take many forms, including sound waves, all those things. Signal and come to that here exact point, audio and speech processing, image enhancements, radar and sonar systems also. So, I can see that what's the process is making into the matrices. The goal is often to extract meaningful information, reducing noise, compress data, transform signals into that more useful from further analysis of decision making. Signal representation, transformation, vectors, and matrices are used to visualize and manipulate signals, applying various transformations for desired effects. And filtering, especially matrices, represents filters used in signal analysis or reduction of the noise. Finally, frequency analysis. Linear transformations like the Fourier transformations are essential for breaking signals into their constituent frequencies. Dimensionality reduction is very important even in image processing also. So now you can see that here linear algebra reduces the dimensionality data by projecting high dimensional data sets onto that lower dimensional subspaces while using the maximum variance. Combats that curse of dimensionality, prevents the models from being computationally overloaded or overfitting due to many irrelevant variables, reduces that computational of machine learning models. Finally, data visualization transforms a high dimensional data from 2D to 3D plans, so human can actually see the patterns also. And noise reduction, it's very important. By ignoring the dimensions with a low eigenvalues variance, you will naturally discard some random noise that does not contribute to the overall signal. Continuing that same dimensionality reduction, we are going to use that PCA method, SVD, LDA, linear discriminant analysis, and matrix factorization to reduce the data. Going on to that, one more application, computer graphics. So transmission. This also we have done in the class. Desmos using the app, right? So translation, which is called that rotation, which is called scale. This is called scale, scale. So it is vital for 3D modeling, allowing for the rotation, scaling, translations of objects as well as the rendering and mapping 3D objects to the 2D screens. You can see that all those things. Digital image processing. So we have taken that this image. Computer stores images as a grids of numbers. These are all the grids dividing like this, say squares. Every action from beginning to that photo recognize the face is essentially a series of matrix operations. Image presentation. Digital images are treated as a matrices where each element represents a pixel's intensity. Color image is a typically tensor 3D matrix with three channels like red, green, and blue RGB. You can see that here also RGB only. And geometric transformations operations like translating, rotating, scaling, sharing are performed by multiplying that image coordinate of vectors by transformation matrix. So this is called translate and this is called rotate. So you can clearly observe that what's the translate is going to do. You can clearly observe that what's the rotation. So these are things. And this is called scaling. Increasing, not increasing, scaling. Sharing. Okay, you can move on to that left or right like this. Next, digital image processing, the same containing image filtering and convolution, blurring and share, sharpening, edge detection are achieved through the matrix convolution. The small matrix, as known as a kernel, is a slid across the image and recalculating pixels values to that highlight specific features. Image compression will be using SVD, like linear algebra technique used to compress images. It breaks the large matrix into simpler parts, allowing the computer to discard less important data while keeping into that image techniques. So, hope I think in today's class we learned that many applications. So, what you understood using that this CBC course beyond that curriculum. See, whatever you learn in a first year, the core concepts like linear algebra, that you are going to use in stats also, right? So that's a thing I need to give that the both the subjects, how the linear algebra is converted in are using into the stochastic process also in advanced thing using correlation, regression, test of hypothesis, whatever, right? So in today's class, we learn about that what's the applications are. These many applications are there in real life, right? So you'll get that one confidence by seeing that all these. I'll send you that this notes also. You put in the drive, and you can see that the recording sessions and the notes also that will be useful in further uh, third year and fourth year. And after completion of BTech also, we can you are going to see that many things applications in your daily life. So hope you understood that all the basics and the applications, whatever the concepts today's we discussed. We will see that in next CBC class too. Thank you so much.